I think a lot of people don't understand where water comes from, and they say it is rain. We get rainwater, right? And the water hits the ground, and it either goes under the ground, it goes over the ground, it might go down across the ground, it might dissolve some things, it might not dissolve some things. When things get dissolved, you can't see them. You can't see them in there. And then the water goes into rivers, and then how do we get water? And we actually do take that water. We take that water that comes out of rivers and streams, and we treat it. Now, when they treat it, the first thing you have to do is any large objects have to come out. So if there's any logs floating in the water, they have to get rid of those, sticks, stuff like that. So that's the macro, get rid of that stuff. Then you got this other stuff, and you say, what if there's like solid chemicals, solid things in there, but not logs? Well, they got to get rid of that. And then they have this stuff leftovers water, and it's got all kinds of stuff in it, and we don't know. And we need to know what's in the water before we put it in the water tower and say it's okay to drink that stuff. Most places, how many of you have gone on missions? Any of you gone on missions or anything like that? Where have you gone? Where'd you go?
I've been to Guatemala.
You've been in Guatemala? Oh, yeah, that's it. All right, where'd you go?
Sorry, it's classified.
Okay.
Florida.
Florida? Okay.
Panama.
Panama? Okay. So if you're outside the country,
Just like
is it okay just to, at Panama or Guatemala, just go get a drink of water somewhere? Is it? Why? What's the problem? When they come to our country, can they turn on the faucet and get a drink? So we kind of take that for granted that the water that we have is some of the cleanest, some of the cleanest water on the planet. And I would be careful going to any country and just drinking the water. All right, so take a look here. There are people who actually take samples of water and they test it. Now, how do they test it? What are they looking for? It just looks like water. And if you'll take a look, here's some things they test for. Here's one, fluoride. What is the level of fluoride ion? I can't see fluoride ions, but they're in there. And so, what about chloride? Aluminum, I don't see iron here, but here's some more sulfate ion. Here's a pH, here's iron. And they test for different things like that. They even have their tests for heavy metals like cadmium, mercury. They have tests for that too. But there's a group of people, thousands of scientists work for the EPA, the Environmental Protection Agency, and they have scientists all the time. They've already done a lot of these things, and they want to know what is the level at which you can accept these chemicals in the water. And you might be saying to yourself, I don't want any lead in my water. You could say that. You could say, I don't want anything in the water except water. But it would cost a lot of money to do that. And as soon as you put it in pipes, it's going to pick up some other stuff too, isn't it? So it's almost impossible, unless you buy it at the store all the time, to get water that has nothing in it except water. So then the EPA says, well, what are the levels at which we can accept these? And that's well established. And so Greensboro's water treatment plant, they have to test them and say, what is the level of iron? And over here, if you'll see, here's the units. It's in milligrams per liter. And it says here, what's that say, does they say 55? Okay, highest allowable level. Ideal goal in, I forget what those units are, per liter, per gram maybe. They shouldn't use capital letters like that. Okay, and then anyway, you'll see these different ranges. See down here the range? And that says if you're within that range, then it's okay to put it in the water towers and people can drink it. So they've done studies saying that at this level, you get the same results on living organisms as you would if there was nothing. So it's almost as if there's nothing in there, even though it's not. Okay, so these are almost everything in here is in solution, isn't it? Now, we don't live next to the ocean, but if we lived next to the ocean and let's say you had a thriving fishing industry or lobster industry like in Maine, how long can you wait before you figure out that something's poisoning all the lobsters in Maine? How long can you wait? Do we wait until a whole bunch of lobsters come up dead? Can we wait that long? they have to be able to know if there's a trend, is there something happening in the water that's going to eventually kill fish or kill other things, crabs and stuff like that, clams. And so they hire a whole bunch of marine biologists all along the coast, and what they do is test water. So they'll go out and they have different things. They'll go out on their little boat, and they'll take a sample, and it'll go down a certain number. They have a standard depth, and they take the water from there, and they take the water from there, and then they take it back to the lab, and they test it. Now, the good news, the way they used to test it, it might take more than a week before they could do all the chemical tests and this, and they filter, and they make precipitates and weigh them and dry them. But today, almost never is that done. Today, almost everything that's analyzed is done almost instantaneously. One of the labs you're going to be doing in the second semester has to do with spectrophotometry. And that's where you can actually measure a chemical in solution without doing any real chemistry. You just let light go through it. You let light pass through it, and the instrument is able to measure the light going in and compare it to the light going out. Now, at a certain wavelength, let's say the sulfate ion. The sulfate ion might absorb wavelengths of 500 nanometers better than anywhere else. So we might use 500 nanometers, shine it in there, and say, hey, we had this much light going in, but only half of it came out. There must be a lot of sulfate in there because it's absorbing the 500 nanometer light. Does that make sense to you? And so when you do spectrophotometry, we'll talk about the whole theory, how that works. And so most of the treatment plants do that. They take a sample of the water, and they open up their machine, they set it to a certain wavelength, they pop it in there, get a reading, look on the chart. All right, they know exactly how many parts per million that's in there. And now that's very quickly. So they do it, they might do that several times a day and say, the water's good, the water's good, the water's good. And we kind of take that for granted, don't we? We take that for granted. We turn that faucet on, that somebody has been testing that water over and over. Those people along the coast, I was talking about, the fishing industry, they don't know the science behind it, but they like to be told, hey, you know all those fish you caught yesterday, don't sell them. There was an unusually high amount of something in there, some kind of poison. So don't sell those to the stores, the different restaurants. So they kind of depend on that. That's why they actually have lots of marine biologists that work along the cities along the coast. All right, you okay on this? All right. So this, I think what I like about solutions, I didn't know a whole lot about them. I would say it's very, very big business. If you like the business end of chemistry, it's huge. This place in Burlington called LabCorp. How many thousands and thousands of samples are sent there every day, where people get their blood tested, their urine tested, or whatever, and they test that stuff, and they have to be absolutely sure of the results. When I tell you you have too much iron in your blood, then the doctor has to do something about it. So they have to trust those results, don't they? If I say you have copper, you're being poisoned by copper, then you're going to have some kind of medicine, and that's going to have side effects and things like that. So some of these companies, I would say a lot of money goes into measuring things that are in solution. Okay, have you ever thought about, maybe you haven't thought about this, probably 70% of your body is water. Now, that's interesting to me because water is so good at dissolving things, and when you dissolve ionic compounds, they actually break up into ions. Aren't they? They're in solution. Think about that. How much of your physiology, how much of the way you works is because of ions in solution? Have you guys, you haven't done this day, nobody's in anatomy, right? Nobody's taking anatomy? Right. Have you studied, you're doing are you doing cells right now? Have you done anything with ions yet? Okay, so do you guys know how the nerves in your body work?
Electrical impulses.
Where's the electricity coming from? Do you plug it in somewhere? How do you get electrical charge? Think about it.
In your body.
And when you take, some of you will take biology, and you'll find out that across the membrane, there are ions that will move this way and ions that will move this way. And the cell has the ability to actually push certain ions out and bring other ions in. They're all in solution. But when you get a difference in charge, you can send electrical signal. And these nerve cells do this all the time. How about your muscles? How do your muscles work?
Electrolytes.
And electrolytes are ions that are in solution, aren't they? And it's the same idea. Certain ions move one way, certain ions move another. So your body, things that are in solution in your body, that's how you actually work. So if things get out of whack in the ion level, then that happens. That's a problem with you. I had a medicine I was taking. I've been taking certain medicine for over 20 years, but they have to check once a year, and had to do with blood pressure. And yet this one medicine has a tendency to pull potassium ions out of your blood. So they have to check every year, and if my potassium ion level goes too low, that could cause a lot of problems. And now so far it hasn't, but if it did, I'd have to take a supplement. I'd have to take a medicine to actually put potassium ions back into my blood. So anyway, if you're going to become a doctor, if you're going to get into chemistry like this, the idea of ions are way more important than you think. Everything else we've done so far is important. But I think this is what's going to make the difference as far as, what if you're a researcher or something like that? You'll be surprised how ions come into play more than anything else. So let's go ahead and get started. Let's take a look here. One thing that's bad, you remember in physics, I told you what's the one thing that was kind of bad about the air pressure? You remember air pressure? What was kind of bad about that? How do you measure air pressure? What's one way you can measure air pressure? You remember that?
Pounds per square inch.
Pounds per square inch. What else? See how many you remember.
Grams per square.
That would be density. Oh, yeah, per square. I could do that. Probably newtons per square meter. That's called a Pascal. Newtons per square meter. You had atmospheres. 1 atmosphere, 2 atmospheres. Bar. There was torr. There's anyway. That was a bad news about pressure. There were so many ways you could measure it. Look at concentration. There are a lot of ways of measuring concentration. So let's take a look at this one right here. This one is in grams per 100 grams. Oh, what is that? Well, in a solution, what do you call the object, the chemical that gets dissolved? What is the chemical that gets dissolved called?
Solvent.
The solvent or solute? So if I have a little bit of salt and I put it in a gallon of water, the salt is the what? The salt would be what? That's called the solute. And what is the thing that does the dissolving? Help me out here, okay?
Solvent.
All right, so let's take a look. One way that you can measure this is called grams of solute per 100 grams of, what's it say, solvent. Now, this is kind of an unusual concentration unit. I'm trying to think if there's ever used except for this one really big thing. And if you look back there, can you see that graph that's way up in the air back there? It's got a blue, it's got a solubility graph. We're going to take a look at that this chapter. About whoever did that experiment a long time ago said, hey, why don't I try to put 1 gram of NaCl in 100 grams of water? Does it dissolve? And they said at room temperature to dissolve. And then they said, let's put 2 grams, let's put 3 grams. And then they found out that there was a max. There was a maximum that you could dissolve that at room temperature water in 100 grams of water. Well, then they made a big study of it, and they said, why don't we change the temperature and do the same thing? And so we know that's what that graph is. It's how many grams of solute can dissolve in 100 grams of water, in this case water, at a certain temperature. And that's one of the most famous graphs in chemistry. I'm still surprised when I used to teach in a public school, every time they had an end of course test on chemistry, what's the one graph they almost always had? It was that one. Because if you can understand that graph, it means you know how to, quote, read a graph. And that's what they were trying to say. Do you know how to read a graph? I don't know if the kids necessarily knew exactly what they were talking about, but could they read that graph? So I will tell you that I know that the solubility graph uses concentration units called grams of solute per 100 grams of solvent. But I don't know any other place where they use it. But it's here to stay. I can't get rid of it. Let's go to the next one. How about this one? Percent by mass. Grams of solute per 100 grams of what? Not solvent, but solution. So if I put 5 grams of salt and 95 grams of water, what would I have? If I put 5 grams of salt, 95 grams of water, I would have 5 grams of salt in a total of 100. That would be called a 5% solution. Now this one actually is still used a lot. When I was in biology in college and we made solutions, it was almost always this way. Now I want to tell you this. I'm not an expert on this, but why do the biologists still tend to use these units here? Here's my idea. Number one, what kind of equipment do I need to make that solution? A balance. That's it. Give me a bowl. Give me a cup. I'll put the salt. I'll weigh the salt. I'll weigh the water. I'll put them together, mix it, and there I got a 5% solution. It's very simple to make. You get it? You don't even have to like chemistry, and you can make a 5% solution. Now, I'm not trying to tell you that biologists don't like chemistry. But on the other hand, they have their own little world that is a little different than the chemist world. So this is grams per 100 grams of solution. This is called percent by mass. And the word percent means per 100, doesn't it? So out of 100 pieces total, 5 of them are salt. Look at the next one. This is grams of solute per million grams of solution. That's not parts per 100, not percent. What would this be called?
Parts per million.
But it's the same idea. Notice it's still an idea of percent. It's like percent, except it's parts per million. How about parts per billion and parts per trillion? Believe it or not, there are chemicals that are so poisonous, you have to keep track of them in parts per trillion, like plutonium. I can't have too many parts per trillion of plutonium without having people get hurt. So this is a very, you almost say, why would anybody have to measure parts per trillion? Well, it must be a chemical that is very bad for living things. You get it? All right, so all these are kind of together, aren't they? Look at this right here. All of these are the same idea. Yes? This is its own idea, but I only see it on the solubility graph. And here's the king. Here's the star of the show in chemistry. This is the one you're going to use more than any other. It's called molarity. Now, what's interesting is you might say to yourself, why do they need another concentration unit? Why wouldn't this cover pretty much anything you wanted? I could, you're right, I could make any solution I wanted with this idea. Why do I need a new one? And it gets worse than that. Look at the definition they had. It says moles of solute. Moles? Oh, now I gotta know about the mole idea, don't I? Moles of solute per what? Liter of, not solvent, but solution. You say to yourself, wait a minute. Wait a minute. Let me give you something here. If you're going to use that definition, wait, I have to have more than a balance. I have to have more than a balance. And it's okay, so I got to figure out, let's say I want to make a 1 molar solution, okay? What if I want to make a 1 molar solution of NaCl? Can you tell me how many grams of NaCl I would need to have a mole? Parker, what do you think? How many grams of NaCl do I need to make a mole?
Probably 150.
Well, we just had a chapter on this, but What if I said, what's 1 mole of NaCl?
57.
What's the molar mass of NaCl? 50, what is it, 50? So it's 23 plus 35.5, isn't it?
I get that.
So 58.5?
Yeah.
Okay, now I have to have a balance. I have to know about moles, okay? And it gets worse. I can't just weigh the solute and weigh the solvent, because that's not what your definition says. It says per liter of solution. So let's say, now this one, I couldn't find the liter one, but this is a half a liter. So let's take half a mole. Let me put half a mole of NaCl in there, and then I put water in there. Well, what's the mass of the water in there? How much water is in there? And you might say it's half a liter, but that's not true. The salt took up some space, didn't it? So how much water's in there? I don't know. Their definition says when you put that in there and then you fill it up, so the total volume is how much? 1 liter. Wait a minute. Now you're talking about, not only do I have to know the mole concept, now I've got somebody had to invent a piece of glassware that no lab had before you started doing that thing called molarity. No, nobody's going to go for that. Around the whole world, you're telling every chemistry lab that they need to have a new kind of glassware called a volumetric flask. They're not going to go for that. Yes, they did. There must be something very powerful about that definition. Why would you want to get rid of all this stuff here and have to have new glassware? And anybody know the key to that? So I'm going to show you something real quickly. I keep this card. It's kind of funny. I had a person. She was a valedictorian of the class, and it's funny, but she wanted to photocopy. She wanted to take a picture of that, even though we use it all the time. It was just a simple little index card, and it had the 4 equations that we'll use more than anything else in this chapter. Now, I want you to take a look at this. Here's your definition. Molarity, that's called molarity, equals moles of solute per liter of solution. Got that? Now, rearrange that. If you rearrange it, look what happens. Molarity times volume in liters. What is molarity times volume in liters? Moles. And what can you do with moles in stoichiometry? Aren't you right there? Aren't you right there? You have your balance equation right there. So if I start doing experiments with solutions, if I know the molarity and I know the volume, I can get right into the world of moles. And that was so important that every lab in the whole world said, yep, we're going to buy these expensive new things called volumetric flasks. Because it was so difficult to have a 10% solution and said, well, wait, what if I have 3 milliliters of that and 10 milliliters of that? How many milliliters of precipitate should I get? How many grams, I mean? He said, I don't know mole. How do you get in the mole world from here? You can't get in the mole world from very difficult. So that's why molarity is going to be the star of the show, because real easily, molarity times volume equals moles. You're going to find out later that I'll show you how to do dilutions. You guys are going to have to know how to do dilutions. So you start with a certain molarity times a certain volume, and then you dilute it. And you'll have a second volume and a second molarity, and it'll be a diluted. Now, why does this work? Because, look right here. What's molarity times volume? So I got this real concentrated stuff. I have the molarity and the volume. I stick it in another container and add some more water to it. What stayed the same, though? What's molarity times volume? So I took a certain amount of moles out of this concentrated stuff, and then I watered it down, but I had the same number of moles of that chemical. You see that? And that's why this equation is also has molarity as the star. All right. Also, we'll do a thing called acid-base neutralization. That's what your big project is about. Is you're going to make a solution that has a certain molarity to it, and also you'll have to calculate. You'll have to see how much how the volume is, and then I'm going to make an acid where I don't tell you the concentration. I won't tell you the concentration, but you have to figure it out. And so you can use this to figure out the unknown by making your own solution like that. You see how this chapter is really crucial to me. If you're going to be better than most students in chemistry. Okay, so here we go again. This is going to be the star of the show. It's used everywhere in chemistry. Now, I want to tell you about this little guy. I think what happened at one time, somebody said, we need to get into the mole a little bit. We've been doing this stuff here, and that has nothing to do with the mole. And so there was this thing called molality. Now, molality is not the star of the show. See, molarity is capital M, and molality is only little m. And it's a moles of solute per what? Kilogram of, not solution, but what? Oh, that's kind of easy to make, see? Now, if I put 58.5 grams of NaCl, and I put it into a liter of water, is a kilogram of water, isn't it? Then, there you go. See? I need that. So I think, in a way, it was an attempt to get into the mole world and not have to worry about that. But why do I even teach this at all? This is going to be so minor. I might have one question on your test, okay? One. Unfortunately, there's a very famous experiment done, just like that one, just like the solubility one. There's a really famous one that uses molality, and it's in every chemistry textbook, and they're not going to get rid of it. And here's what it is. Did you know that water normally freezes at 100 degrees, boils at 100 degrees Celsius, right? If you have a certain number of moles of stuff dissolved in it, it will not freeze, it will not boil at 100 degrees. As a matter of fact, the more moles of things that are in there, anything that's dissolved, it will cause a boiling point elevation. So instead of boiling at 100, it'll boil at higher. You have to get hotter than 100 to get the water to boil. It also causes the freezing point to be depressed. And so normally it freezes at 0 degrees Celsius. The more moles that are dissolved there, it will not freeze until you get down lower. And that whole study was done in molality. And so I hate to tell you that, but when you get to college, if they say molality, you know it's a minor thing, but it is used for boiling point elevation and freezing point depression. And so, anyway, then you just have to remind yourself what the definition is. But here's the one you have to know for sure. Now, there's another one I'm not going to actually get into in this class. I'm not saying you won't have it in college. I'm not saying you won't. One of them is called normality, and I might mention it to you during this chapter, but it's also a minor character. Many things have a certain normality is the same as their molarity, and sometimes not, but that's a kind of a small thing. One thing I want to mention also, I'm going to link this one over here to these. What if you do percent by volume? That's really the same ideas up here, okay? And we're going to show you how to make. I'm going to show you how to make solutions here. All right. So that's a quick run through. So what you know is this is used in one very special case. This is used in one very special case. This is used everywhere. All right, so spend most of your time on this. And these, you don't have the mole concept. That's really, I know you can understand this. It's not that hard. And that's the same thing as this. All right, so let's, also I want to show you one quick thing here. Here it is. Parts per million. For whatever reason, the author did not put that in bold print in your book. Yet in the study guide, he has it in there, and I don't know why, because parts per million will come up a lot. And so parts per million is also, look at this right here, it's milligrams per 1,000 grams of solution. That's the same as a part per million. Okay, anyway, you'll use that on one of the homework questions like that. I won't really stress that. Okay, anyway, last thing, and I'll turn the page. I know you guys are way more advanced than you were in 10th grade. As a matter of fact, in 11th grade, you got even more advanced. See these right here? Do you understand that the word concentration, you can get tricked? Why did people why did they get tricked with things like density? Why is it that the density of a piece of iron is 8? What's the density of half a piece of iron? It has to be 8. You don't want to say 8, but it is, right? It's a ratio, isn't it? What's the slope? What's the slope? What's the slope of this line down here? Let's say the slope is 3. Ooh, what happens to the slope when you get up here, though? It's 3. The slope for a straight line is a constant, isn't it? So any linear relationship is constant everywhere along that line because it's a ratio, isn't it? So the world of ratios, you do have to be careful about that. So just like density, just like pressure's a ratio, and so is concentration. That's why you get 2 units, don't you? 2 units like that. All right, let's flip this over. Now the next skill I want you to be able to do is, what if, and I was never allowed to make solutions, and they didn't teach me how to make solutions, but I'm going to do that for you guys. You guys are going to learn to make your own solutions, and I think it'll make sense to you, but as we go through here. Look at the first one. Tell me in words, how would you make this right here? How would you make this? And I want you to kind of act like it's a cookbook, and I'm going to follow your directions, okay? And if you have to do any calculations, you can do them over here, but let's take about 1 minute. And if you want to go ahead and move next to somebody and sit with somebody, I'd like you to say, all right, tell me what to do first. Tell me, and if you want me to use a beaker, say beaker. If you want me to use weigh something out, tell me that. All right, go sit with somebody, and I'll give you 1 minute to see if you can tell me, how would you make this if I said tomorrow, that's a quiz grade, all right, here, go to it. Make this for me. All right? Parker, you can move it anywhere you want. You can move it either one.
Okay.
All right, how you going to make it? So if you're in a biology class in college and they said you have to make a 20% solution or a 10% solution, you know what they do in college, though? You know what they do in... Uh-oh.
I think
Goodbye.
we're kind of late.
Goodbye. Go to chapel. I am very sorry. I am very, very